conversation with Trevor probably a few months ago, and he thinks maybe the topic we are doing NICTA is interesting. So although I have a title called Performance Management and Asset Planning and Continuous Change, actually, I'm not here telling you how to do this, but rather than what we do may generate some interesting discussions around how it can help, or on the other way, how performance management and capacity planning can help us answering some of our questions. So feel free to interrupt me any time. The slides are actually already on slide share if you want to access them during the event or afterwards, just enter my name. So I have my colleague Dr. Ingo Weber here as well. We are both researchers at NICTA. We also are associated with the University of New South Wales. So we teach courses over there and we supervise students as well.
Excuse me, NICTA is
NICTA. What does NICTA stand for? So NICTA stands for National ICT Australia. ICT, of course, is Information and Communication Technology. So it's sort of Australia's National Centre of Excellence in ICT research. It was founded around 2002-2003. Both we get funding from the federal level and the state level. So that's why we have 5 research labs. We actually have a research lab in Melbourne. We also have Australian Sydney. In Sydney we have 2 labs. One is very close to UNSW, the other is the Australian Technology Park, Canberra, and Brisbane, basically. It's sort of like, you may know CSIRO, and the CSIRO have ICT Centre, ICT Research. We are just sort of more of a dedicated research center. And the CSIRO ICT sometimes do ICT research for a lot of the major industries in Australia, mining and water, agriculture. But we are more sort of doing ICT research for its own sake rather than supporting another industry. So that's sort of the differentiation between us and CSIRO ICT centers. We have around 700 staff, including everyone, across these labs. And currently, roughly have 270 PhD students who are graduating, maybe 50 of them every year. Budgets sort of 1 million operating. And we generate research papers, spin-offs, licensable technologies, and things. You are welcome to visit any of our labs. Just contact me. Because we are always also looking for industry collaboration. So within NICTA, we have roughly university partners. All the students are coming from the University of New South Wales, University of Melbourne. We have roughly 5 or 6 research groups. As you can see, I'm from software systems, which is very big words, broad words, doing all sorts of stuff. I'll talk about what we do a little bit later. But we also have people in networks, optimization, machine learning, and computer vision. So that's for research excellence. We publish papers and produce advanced research or technologies. On the other hand, we have industry and government partners. And roughly in the areas of broadband and digital economy, infrastructure, transport logistics, and security environment. The goal over there is for wealth creation, of course, spin-outs, licensable technologies, anything of impact through helping Australian companies, SME to big companies, that's wealth creation. So back on what, in particular in our group, software system research group, SSRG, our vision is cost-effective, dependable systems. Dependability, I don't know how many of you are interested in dependability, but dependability is a kind of umbrella word for a lot of the reliability, availability, performance, security. The group together probably called dependability. In our group, we have 2 major activities. One is trustworthy systems. We focus on operating systems, microkernels. Actually, you might be surprised to know if you have the latest iPhone or any of Android devices, our technology, microkernel, is run inside of your phone. It's run in 1 billion mobile phones in the world. That's sort of microkernel is very small, 8,000 lines of code. but it runs in your chips, clockwork chips, providing a lot of the modern communication capabilities there. So that's the trustworthy system, single system microkernel part. The other half of our group is doing dependable cloud computing. That's sort of more multiple box distributed systems. So I'm from the dependable cloud computing part. But these two parts work closely together because it's all about building dependable systems. A little bit of history on what we did before, because I think the audience is interested in performance management and capacity planning. Actually, we had a long history in this, not exactly what we're doing right now, but many years ago, we had tools like Validate and you probably never heard of this, but because it's a research prototypes, which what it does is it does automatic benchmarking. If you have a very big application, we will abstract that big application into a smaller application, which represents the characteristics of the big application, context of the application. Then we run this smaller application flag benchmarking and monitoring metrics, and then we use things like queuing models and other analysis models to predict your big application's performance characteristics. So that's why we call it the regulator or NBA bench. I think this work was introduced in one of the early CNG conference, probably in 2006, and one back report or something. So that's another life, obviously. We also have a spin-out out of this work, and not exactly out of this work, but from our group. If you go to assurance.com, people are still there, based in Canberra, doing a lot of government performance stuff. We are actually on spec. Everybody here knows about spec, how the benchmarking work. We are a group research group member. I'm representing it actually on the board of spec. People at this stage interested in cloud benchmarking, and a lot. We propose elasticity benchmarks to the cloud research group at spec. And finally, ICPE is International Conference on Performance Engineering. It's actually happening right now in Europe somewhere. I don't know where this year. Last year, one of us from our group went to give a keynote talk supporting operation personnel to performance engineering. So today's talk actually you will see a little bit is still in this operation personnel space. This is just a history, and that's why we still have our capacity planning and performance benchmarking in our DNA, and we still do a lot of work. But in particularly, what we are dealing right now is we see the new challenge in dependability and in performance engineering. In particular, is this continuous change. More and more companies are doing much shorter release cycles on their software. You heard of the word of DevOps, continuous delivery, continuous deployment. Before we're doing all this kind of thing, every few months, and probably you will do this, your performance planning cycle several months. You have a new application coming in, you estimate your capacity, then you release it out. But this is giving you an extreme example. For example, is called the eBay for crafts. Website, very big website, millions of customers. They do 25 full deployments to their server farms of thousands of servers, 25 times a day. And basically every 10 commits in your software is being rolled out to an entire system. And how do you do capacity planning for this? Does that have any of the new release, whether it's having new impact on the performance plan and management of capacity? You don't know, you have to do it continuously. Also, a lot of the people, companies are using cloud. So in cloud, everything is called elasticity, resource sharing. And you have a lot of things going on. For example, in cloud, you can scale in out. Sometimes for backup, you take snapshots, you migrate stuff. Providers may migrate stuff. And then you do reconfiguration, rolling upgrade, you have cron jobs. There's just a lot of things happening. And you have resource sharing. You don't have the luxury of a dedicated machine, properly benchmarked. And even these days, you request for variance of the virtual machine you are getting, even you are asking the exact same configuration, the one you get operates slightly differently in different conditions. And in cloud, you know, especially if you use public cloud for some of your work, you have very limited visibility on what's going on under the hood. And if you want to do something, you have full control. You can call a few APIs. You can ask for a new virtual machine, but that's probably all you can do. Rather than tweaking under the hood like many performance engineers. So how can do your job when you have no control? But that's sort of the inspiration of this work. But you would say, so maybe I'll give you an example. So we are talking about sporadic operations and other things going on. So one example is we call the rolling operation. So imagine you have 100 servers in your server farm, and you have some version 1 software, and you want to upgrade 10 servers at a time to version 2 software. And because in this way, there's no time, no downtime, and there's no additional redundancy cost. But it can potentially take a very long time to complete. And if you do it 25 times a day, it would be ongoing forever. And you finish one, you have another coming. And you may have errors during operation, and you do have other things going on. I know this scenario doesn't work very well in a lot of banks or financial institutions. Probably you guys are still doing, many of you guys are still doing green box. You have your full sort of a redundancy, replication of your environment, and you can test your new software. After you're happy, you switch the load balancer to the other one. But the world, especially in big, large-scale web operation, is moving towards this, and in cloud, it's moving towards this kind of situation. So I'm not going to the right. This is how you do it in Amazon Cloud. Amazon Cloud, you have all the scaling groups. So for this kind of thing happening in Amazon Cloud, using all the scaling group, you just you find all your instances, you remove them from the last load balancer, you terminate them, you wait them to come back, and you re-register them into this as a process. So what happens during this scene? If you don't turn off your monitoring, or you try to still have your normal monitoring performance data collected, and you will see when this box is basically indicating the time when you are doing this type of thing. Of course, you have a CPU utilization going up slightly, and you have somehow maybe network out, I don't know why network out down there is also spiking a little bit. But on the other hand, if you're monitoring of the health of your system, if you have monitoring set up, it will go berserk because things are going down. And you deliberately killing them, but of course things are going down. So unfortunately, I heard sometimes when you do system upgrade or major changes, operators turn off our monitoring, turn off all alerts because you get notified. But that's also the most vulnerable moment of your system. Your system is being changed a lot, and you are turning off everything because you want to hear all these false positive alerts. So that's a problem we observe. So what's our overall approach? Our overall approach is to incorporate all this change-related knowledge into system management. So first is the sporadic operation knowledge. We propose something we call POS, Process Oriented Dependability. I'll go into it a little bit. Tonight, we didn't cover that part. That's for error detection and diagnosis under this continuous change. I talked about alerts, false positives. So once you have this process knowledge, you can pretty much do a lot of alerting management, suppressing the false positives using this process context. And probably a lot of people are interested in the availability or the performance during this sporadic operation, if this happens all the time. So there might be over there. And also, not only you have sporadic operation knowledge, you may have external event knowledge. And many people here are probably interested in local prediction. And I'll talk a little bit about the event aware local prediction right now. So let's quickly jump into this process-oriented dependability. So the context here, a lot of them is really large-scale web operation, and we are also diving into this distributed data analytics in the cloud. We have Hadoop clusters, you have Spark clusters running, and things are changing a lot, and you're sharing resources. So really, it's about detecting problems during the sporadic operation, not the normal operation that most of people are familiar with. So the key idea behind this is you see an operation as a process. And how do you know this process? Basically, we have doing this in two stages. The first stage is offline. We discover this process so automatically from logs and scripts, because all these operations are basically a bunch of scripts running and produce logs. And we can use automatic ways of clustering them and defining this process. And for each of the steps, we may figure out the expected step outcomes specified by software assertions. Then, during runtime, we use this information. So process context is what sort of process is running, whether it's rolling upgrade or it's scaling in, scaling out. We have process IDs. If the process have several steps, we have step IDs. We have expected states of each steps. Then we can detect errors by examining, basically by using the assertions and compliance checking against the discovered process in terms of sequence of logs, missing log lines, to find problems. I'll go into this in detail in the next few slides. Once you do the error detection, then you can further diagnose problems. I know these days when you have a problem, probably you have an interactive dashboard, Splunk, log analysis, whatever, you dive into the problems. Then you run a few commands here and there, SSH to here, there. We are here after we know errors and we know the process context, we can do a little bit automated diagnosis test. You can automatically do a lot of things you will do anyway by manually. You can find a little bit more details in the paper we recently published at the conference called ESN. But for example, if you will use rolling upgrade in the cloud world, a lot of people are using a tool from Netflix called Asgard. Netflix is the US movie streaming company, and they open sourcing a lot of their tools because most of their stuff is running inside Amazon. Once the CEO of Netflix told the audience to say, we are not a movie streaming company, we are a monitoring company. Because imagine all their logic, all their smarts, all their competitive advantage is in monitoring from user behavior to how their software is behaving in AWS and making sure everybody don't have jittering movies being streamed. So all their technology is on monitoring. And their encoding and their movie rights is just a small part happens to be. So we do performance engineering. Imagine the whole company is about monitoring, even they are multi-billion-dollar company these days. So we use Asgard. It's a bit off topic. We use Asgard produced by Netflix. Asgard produces log, and we do process mining, automatically discovered processing. The operator may have to do a little bit of inputs, but it's once off. After you do this, for Asgard, you don't have to do anything more. During runtime, Asgard allows printing out new logs, and we will use this discovered model to do error detection, and we notify operators. So the detection part actually has two parts. One is we call assertion check, the other is called performance check. Let's go into a bit details on how this assertion checking works. It's very simple behind the scene. Basically, say if you have this model on the left, which you have discovered, removing something from ELB, terminating something, wait for ES3 to start new instances, and you see a log line removed. Because in cloud, a lot of things are very uncertain and takes a long time to finish, terminating something or start something, or even removing something. The traditional exception handling doesn't work very well. It's not like you always can wait a blocking and do something. So we do independent assertions. Because internal actually, Asgard does very little exception handling. Sometimes you just wait for an hour for something to finish if it doesn't finish within time. So we do independent assertions on the side to see whether it's indeed deregistered, whether it's been removed, how many instances of version 1 is now running, monitoring. Okay, it's not only one-time checking, we can periodically guarantee some assertions and invariance of this. And you see another log line says terminating something, and we will assert something has been terminated indeed. The next log line is on waiting about something. Historically, we automatically mine from the log line that most of the time, the average is 60 minutes to finish. But 95% are finishing within 17 minutes and 35 seconds. That's automatically calculated. And we can just assert the next log line should appear within this. If you don't do this, SQL actually will wait for an hour and 10 minutes. This default configuration doesn't make much sense in this scenario. So then you have new instances growing up. Okay. So this is another way of checking. We call it conformance checking, because you have an instance of this process running, and you have a process model. Of course, you can see whether the instance is compliant, is conforming to the process model. So at the very beginning, we are basically doing token counting. So in our system, we have a token. The token, when we see a log line, we move the token to the next activity, indicating the last one has been finished. Now it's at the second one. And then we see terminate, we move the token again. Then we see wait, we move that token. Actually, we are expecting the next log line to be used instance that has been registered. But suddenly, we see another terminate. So you have a potential problem here. I mean, you don't know what happened, but you know we're expecting a log line, new instance is registered, but you're getting terminated. So in a way, first you don't know what's happening. You don't know what's happening to the first token. But on the other hand, you can probably insert another token to say something else has been terminated, and you will probably be waiting for another instance of wait to come up. And you probably increase the error counter to one, add one to the error counter. Something has not normal. Yeah. So that's how we detect problem using performance checking. So this is a single slide just telling you, once we have this error detection, what do we do? It's probably you can see from, this is a fault tree for people who are not familiar with fault tree. So at the very top, the system is expecting some states. And if any of these things go wrong, it contributes to that false. But this thing can go wrong also because of this reason, and this can go wrong because of this. So it's a tree structure. This is probably the thing you call root cause of something going wrong. If something going wrong at the very top, you have to do a lot of checkings, going through logs and here and there, ping here, check logs over there. But if you know the process comments, look at this. This kind of nodes are indicating the thing you just discovered. You can prune the fault tree pretty quickly to narrow down to say, oh, something happened here. It must be one of these two reasons, for example. And you immediately do an automatic diagnosis test. No human intervention. You probably can figure out a probability of something going on somewhere. So we use this process context in this scenario. Okay, so I'm not going to talk about this slide, this sort of evaluation of this. We've run many experiments and see how it works. I mean, the diagram here really shows for diagnosis time, most of the time is retained within 4 seconds. And with a very, very high accuracy rate in terms of accuracy of diagnosis, recall of diagnosis, precision of detection, or different kind of errors. And some of them, of course, around 80%. A lot of them are 100%. So this is kind of a pod story. Let me move on to the next 3 things I'll briefly mention. Yeah, please.
So, do you build is the main thing about pod is building that fault tree?
A fault tree, well, this is reusable knowledge. You probably build once. This knowledge is basically what can go wrong in Amazon Cloud in terms of API you call the systems you probably build it once, but of course if you find something new, you can add to the fault tree. It's a knowledge base. So our system is doing all this sort of thing, but it relies on this knowledge-based fault tree for diagnosis. And the detection part doesn't use the fault tree at all. Detection uses basically assertions and performance checks.
And you've got to teach it about what was it, Asgard? What's it called?
Yeah, Asgard. Yeah. Okay, so just briefly go through the next three things. Maybe a bit relevant. So, as I said earlier, a lot of people when they're doing sporadic operation, they say, oh, we have to turn off everything because it's going to, all the alerts going to go berserk. We say, do not turn off your alerts during sporadic operation. Why don't we just dynamically suppress some of this using the operation knowledge? So you know you have a process, probably CPU is time sensitive, another one is network sensitive, another one is IO sensitive. You have all this knowledge. And when you see something happening, probably you will have you raise the alerting threshold a bit higher. So this is your normal operation alerting. And you raise it a bit higher, and you check whether there's really something going on behind the scenes, and you can suppress those. Reduce the false positive from alerts. And also, I think very importantly, probably to this audience is you add context to system monitoring data for later domestic planning and performance. Because otherwise, probably this data around here is not very useful anymore because it was being polluted because it's very noisy, because there are things behind the scene. But you are also interested in this part, because this part is a part that your system is especially vulnerable, and you want to prepare for this part. And if this is happening all the time, rather than middle night every 3 months or for 2 hours, then this becomes a very important thing you have to do. So this is going to an availability analysis for sporadic operation. Remember, I said your system needs to do backup, maintenance, recovery. Before, if it's not continuous or happen in a high frequency, probably don't worry too much. But all these days, it's happening all the time. So what we are doing here is we use something called stochastic reward net. It's a notation for modeling mismatch measurements. And we build a model around all these sporadic operations to see how it's impacting the SLA and what sort of backup recovery strategies, even your deployment application. And your historical data, of course, is used for populating these models. And for example, at the top is a very simple cloud deployment on AWS. You have a load balancer, you have a lot of stateless virtual machines in one zone. They are having a lot of stateful virtual machines in one zone, and you have hot scaling across zone, you have hot standby. And you're taking snapshots a lot and moving them to another region in case your region A is down. And these snapshots are constant, like every few minutes you're taking them. So how this all the operations, the backup, the snapshot, the auto scaling is impacting your availability. We turn this model into an SRM model. You don't have to know details. Then we can analyze things like answer questions like what if your auto scaling threshold is set to be 60% and you have a one zone deployment? What's the availability? How many lines you have? And what if your recovery strategy with different configuration of RTO and RPOs, is that recovery time objective and recovery point objective? What's the impact of the availability? So a little bit of analysis for these sporadic operations. One final thing I want to talk about is event-aware workload prediction. I know people like to predict workload, but a lot of times there are a lot of external events happening, and all these events really are different one from another. For example, auction events will have a very different profile. The first moment you post the auction, you will have a lot of people bidding, then it will die down, but the final few minutes of the auction closing, you will have a spike. That event probably is different from World Cup, match broadcasting event, when people maybe when they will click on things and when they will be looking for stores. And it's different again probably from product launch event, Apple launching a new iPhone. All these events have its own signature basically. So what we did is we built an event model for types of events. For example, this is an auction. So look, you have an auction that, as I described, the first few minutes have some workload spike, then they die down in 5 minutes. But if you are running an auctionable website, you have auctions starting or ending at all times. At this particular point of time, you have 2 starting, and this is one will be closed at this one. So if you have 1,000 auctions, you will have 1,000 of these spread across your timeline. At any particular time, you can actually predict the workload. So this is a sort of more predicted workload. Depending new options starting, old options ending, you can pretty much have a very good understanding of the predicted workload. So I think that might be useful for performance capacity planning. Okay, so this is all I'm going to talk about tonight. And nobody interrupted, not many people interrupted me, so feel free to ask me more questions. So this is a summary of what I've said. Because a lot of this alerting management stuff, we want some inputs from industry on whether it's useful or how you do it right now, how this can be improved, make it more practical and useful. On the other hand, as you see, we do a lot of log analysis, so we need industry help and collaboration from you guys. We need logs, we need trials of our technologies, we need maybe case studies from some of you guys. What you are doing now right now, hopefully you have to be much better than what proposed here and what hear about it. And actually we are writing